Hello everyone, in this video we're going to talk about arrival times, which is going to lead us to talk about K-Erlang random variable. We talked about inter-arrival time between occurrences or arrivals, and we talked about the number of arrivals within a time frame. Now we're talking about arrival time more specifically. And if you think about the arrival time or arrival process of customers to a store, I'm going to draw that little diagram again here. And what we're seeing here is that this is time 0, and let's say here first customer comes in, and then here's the second and the third, and then the fourth customer comes in, and this is a time horizon, so this is essentially T. We talked about that these are time or inter-arrival times, the first inter-arrival time, the second, and so forth. And let's actually make it more generic here. Let's say that we're going to have K, customer K arrival, and at that point this would be T of K, time between these arrivals. At the same time, we had arrival time, which we call it S of K, right? So arrival time of customer 2 is that point in time, which is this duration. So this is essentially S2. And for customer K, it's going to be here, S of K, that duration from 0 all the way to K, that's S of K. So the question is, how can we write S of K in terms of T of J, or inter-arrival time? So by looking at this graph, you can see that the arrival time of customer K is essentially the summation of all these inter-arrival times, right? All the way to customer K. If you add them up, you're going to get the arrival time of customer K. So what we can do here is to say that S of K, which is the arrival time of customer K, is the summation of inter-arrival times. But from where to where? From T1 all the way to Tk. So the iteration is going to be from customer 1 to customer K. So if we add them up, it becomes S of K, or arrival time. So probability distribution of this S of K, because S of K is going to be a random variable as well. You never know when the customer is going to arrive. It's a random variable. But it is a sum of K IID exponential random variables. Independent and identically distributed exponential random variables, because these are all exponentials. And we call S of K K-Erlang random variable because it follows the Erlang distribution. It's a special case of gamma distribution. So S of K is going to be K-Erlang. K is the arrival of the kth customer or occurrences. So the terminology is we're going to have a random variable K-Erlang with the parameter lambda, and this is the same lambda that we had in Poisson process. It's the average arrival rate. So K-Erlang with the only parameter lambda. If K is equal to 1, let me go back to the same diagram here. If K is equal to 1, we're talking about S of 1, right? And S of 1 is here. It's that duration, S of 1. But here you can see that S of 1 and T of 1 are essentially the same, because we're talking about the first customer, the inter-arrival time and arrival time are both the same. So if K is equal to 1, a random variable is 1 Erlang, which is no different than exponential if K is equal to 1. That's just only a special case when we're talking about the first arrival. And because this is arrival time, again, time is continuous, right? The random variable is continuous. We're talking about arrival time, and that arrival can start from time 0 all the way to infinity, which means that arrival never happens. Any time in between can be a possible arrival time. So let's take a look at PDF and CDF function of k-Erlang. And as you can see here, there are functions of lambda and k, right? So you have lambda and you have k. And this is the CDF cumulative distribution function. The expected value of k-Erlang is k over lambda, and standard deviation is square root of k over lambda. To make this more clear, we're going to look at one example here. Let's take a look at this example. It's the same example that we started this module with, and it's the arrival of customers, and the average rate of arrival, lambda, is 8.6 customer per hour, right? Which we converted to minutes in the previous video. That is 0.1433 per minute. So that's our lambda. And in this arrival process, part A is asking on average, again on average referring to expected value, when. So referring to time, so you know that it's going to be either inner arrival time, which is exponential, or arrival time, which is k-Erlang. When will the third customer arrive? The arrival time of the third customer. So it's always helpful to draw that little time diagram here. We're talking about the third customer arrival. Let's say here's the first, and then the second, and then the third here. So we're talking about this duration, which is S of 3, arrival time of the third customer. And we want to know what is the average of S of 3. On average, how long is it going to take for the third customer to arrive? So we're talking about expected value of S of 3. And that is k over lambda. In this case, k is 3. So 3 over. If we want to talk in minutes, you divide that by lambda in minutes. Or if you want to have your answer in hours, you divide that by 8.6. In this case, we're doing it in minutes. So that is equal to 20.93 minutes. So almost every 21 minutes on average, you're going to see this third customer arrival. So that's expected value of third customer arrival. Part B, what is the probability that it will be more than 30 minutes before the third customer arrives? So probability that it takes more than 30 minutes before the third customer arrives. Essentially, this part of the problem is asking what is the probability that this duration is more than 30 minutes. So how do we calculate that? We want to calculate probability that S of 3 is more than 30 minutes. You know that the best way to do this is to convert this to CDF, so we can use the CDF function in the previous slide here. So what we do is we say this is 1 minus probability of the complement, S of 3 less than 30 minutes. Well, in that case, this is the CDF of k-Erlang, or in this case 3-Erlang. It will be 1 minus, and then the k-Erlang itself, CDF has a 1 minus summation of 0 to k minus 1. So that would be n from 0 to 2. E2 negative lambda x, just 30 here, lambda x to n over n factorial. Well, here this one will cancel this one, and this summation will become positive if you do the math, and you're going to get, I believe, 0.1974 once you do that summation. So about 19%, 20% chance that it takes more than 30 minutes for the third customer to arrive. And that's this part. So in part C says, given that it has been 15 minutes since the last customer arrives, what is the probability that it will be more than 30 minutes from now before the third subsequent customer arrives? So the point of this part is that this piece of information does not impact the probability because with the memoryless property that we talked about, what happened in the past, as long as it does not overlap with the probability that we're calculating, it doesn't matter, because exponential distribution, Poisson process, is memoryless. So what matters is that from now, 30 minutes before we see the third customer arrival. So part C, the answer is same as part B, because the past 15 minutes is in the past, and we're talking about from now. So if you think about this graph, we're talking about time 0 until we see the third customer from now. What happened in the past here, right? Here it says that customer -1 came 15 minutes before. Well, that doesn't matter. We're talking about S of 3 from now. So the answer to part C is the same as part B. In the next video, we're going to look at one example that wraps everything together, and we review Poisson, exponential, and K-Erlang.